Hi class, time for more linear algebra. One of our goals now is to explore the geometry of the determinant. Last class, we're diving deep into subspaces and spans of vectors, like if you have a matrix, the span of the columns, the span of the row vectors, etc. We're going to dive more deeply into spans, and in order to do this, first I'm going to introduce some new notation and a new idea. So this will just make it easier for us to talk about certain concepts. So let's say we've got VI, a collection of vectors VI, indexed by the natural numbers. Let's say I is some subset of the natural numbers. This is going to be called our index set. So say that I is the even numbers, for example. Then VI, such that I is in I, is going to be V1, V2, V4, V6, etc. Of course, we can argue about whether 0 is in the natural numbers and 0 is even, but for now, I think you get the point. If I is, for example, 2 and 3, then VI, such that I is in I, this is just going to be V2, V3, this collection. So I as an index set just allows us to quickly reference a subset of our larger index set, say the natural numbers. All right, with that, let's get going. Definition. If I is some index set, and V is a vector space, then VI, so some collection of vectors in V is a spanning set of V if V, as the name suggests, is the span of these vectors. i.e., every element of V, every vector can be expressed as a linear combination of the VIs. Let's explore this. Example, 1, 1, 1, 1, 1, 0, and 1, 0, 0. I'm going to call these vectors V1, V2, and V3. And my claim is that these form a spanning set for R3. Here's an exercise. Okay, say we've got the standard vectors, if you recall, in R3. E1 is going to be 1, 0, 0. E2 is 0, 1, 0. E3 is 0, 0, 1. So first, show that E1, E2, and E3 is in the span of V1, V2, and V3 defined above, right? What this means is just show that you can express E1, for example, as a linear combination of the V1, V2, and V3 with coefficients in the reals. After you've established that, the next thing is easier to show. Show that V1, V2, and V3 indeed form a spanning set. For R3. Okay, here's a question. Say, as usual, A is an n by n matrix. How do we know when the columns of A span Rn? Well, in an n by n matrix, there are n vectors in our columns, right? How do we know when it does or does not span all of our n? So for example, this one that we've been working with, A241, 131, 372, the columns, as we talked about before, do not span all of R3. They span some plane, a proper subspace of R3. So that's one question. A sub-question, of course, is knowing this important? You might think that our question above is just kind of random. Like, why would we want to know the answer to that question? But what I want to point to is that is knowing it important, or is it connected to the other ideas we've been talking about? Inverses, determinants, solutions to systems of linear equations, as you might guess, the answer is yes. And hopefully you'll be able to start sussing this out over the next few lessons. The first thing that we need to make this connection is the idea of linear independence. Definition. Say we've got vectors, v1 through vn, in some vector space V. These vectors are said to be linearly independent. If C1v1 plus Cnvn is equal to 0, the 0 vector, if this implies that Ci is equal to 0 for all I. This is sometimes difficult, so let's run through examples. Example. Say I 1, 0, 0, 0, 1, 0, 0, 0, 1, with the standard vectors E1, E2, and E3 as its columns. Well, say C1, 1, 0, 0, plus C2, 0, 1, 0, plus C3, 0, 0, 1. Say that was equal to the 0 vector. Well, by addition, we know that this is equal to C1, C2, C3, this vector. And by the equality of matrices, how that's defined, this means that C1 is equal to C2, is equal to C3, is equal to 0, because of this string of equalities. So, E1, E2, and E3 are linearly independent. Let's do another example. A is equal to this matrix, 1, 2, 4, 2, 1, 3, 4, negative 1, 1. This is going to be the column vectors A1, A2, and A3. How am I going to find out if these columns are linearly independent or linearly dependent? Well, I'm actually going to pull in an idea, a technique from earlier in the semester. So let's do this. We're going to set up our augmented matrix with zeros on the right-hand side, and we're going to do row reduction. I'm not going to bore you with the details, but I will say that we get this. All right. So just showing that we are remembering that this corresponds to some system of linear equations, we'll know that the first column, second column, and third column correspond to the variables x, y, and z respectively. So here's what I'm going to get from this, that my lead variables, x and y, and my free variable is z. This will give me some guidance as to how to represent the solution. So the first row is going to give me x minus 2z is equal to 0. And the second row is going to give me y plus 3z is equal to 0. So we have x is equal to 2z. And we've got y is equal to negative 3z. And so the solution set will look like 2z, negative 3z, z, where z is some real number. In particular, we've got when z is equal to 1, we have that 2, negative 3, 1 is a solution. And that means that 2 times the first column minus 3 times the second column plus 1 times the third column is equal to the 0 vector. Altogether, that means that A1, A2, and A3 are not linearly independent. All right. Here's an exercise for you. For A is equal to this this matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, are the columns linearly independent? Let's stop here, but I do want to acknowledge many questions that you might have. We just introduced linear independence. So is linear independence of the columns of a matrix connected somehow the determinant of a matrix? Yes. Think on it. We'll talk about more later. See you next time.